Hello everyone, welcome to the Mercury Virtual. Hope you are doing good. Today I'm going to continue with your chapter number 6, that is memory hierarchy, and today is the last class for chapter number 6, and from Monday onwards I will be starting your next chapter, that is chapter number 7, linking. So let's start with the topic that we have covered in the yesterday's class, and today's topic is of impact of cache memory on the performance. This is the topic of today's class. This is impact of caches on the program performance. This is the today's topic. But before that, let's take a quick review what we have covered in the last class. In the last class, we have covered the cache memory in detail. That is the detailed version of the cache memory. Let's take a quick review what we have covered in the last class. Chapter number 6 continued, that is memory hierarchy continued. We have covered the cache memory topic, that is cache memory in detail. This is the memory hierarchy. We have discussed that cache memory is one of the or has the fastest access time after the registers. This is a hierarchy that shows first of all there is a registers, then cache, then main memory, then secondary storage and the offline storage. That the same thing, that is a disk or the tape. So first of all there is a registers, then cache, then main memory and then secondary storage. So this is a memory hierarchy, and cache memory has the highest or the fastest access time after the registers. Then what is the requirement or why is cache memory needed? This point says, or these 2 points says, whenever there is a huge requirement for the CPU, whenever there is a immediate requirement for the CPU, then instead of going to the main memory, CPU fetches the data from the cache memory. This says when a program references a memory or reference a memory location, it is likely to reference that same memory location again and again. That is nearby location or the same memory location. That's why cache memory is very needed for the CPU. Next, one of the main reason is that content of the most commonly accessed locations are maintained can be placed between the CPU and the main memory. When a program executes, the cache memory is searched first. Then why is cache memory fast? Means what is the reason why there is a fast access in the cache memory? The first point says there is a fast electronic used. Why? Because there is a chip that requires multiple chips or that require multiple condensers that is used for the faster access or faster electronics. Then this is again the main reason why cache memory is fast. This is one of the important reason is that a cache memory can be positioned closer to the CPU. That is, cache memory is stored at the closest, or it is required, or it is available at the closest of the CPU, that is between the main memory and the CPU. That's why cache memory is so fast and always synchronized with the CPU with the help of bus. Then we have studied about the cache mapping, that is how we map the contents of the cache memory and the main memory. That is, if data is not available in the cache memory, then the CPU must go to the next place, that is our main memory, and then fetches the data from the main memory and stored in the cache memory. So this technique, this mapping technique is done by the cache mapping, and there are 3 techniques available for the cache mapping. One is associative mapping, one is direct mapping, and one is SET-associative mapping. So there are 3 types of mapping: associative mapping, direct mapping and SET-associative mapping. So first one is your associative mapping. Means there is a associated things, and there is any memory block can be mapped to the any or each cache slot, and it requires or it keeps tracks of the 2 power 27 possible blocks. Then next point says there are dirty bits available, there is a valid bit available that is used to indicate whether or not the slot holds a line or not. Then there is a mapping technique that is going on. This point is important. that we have discussed. If the valid bit is 1 or the valid bit is 1, then the tag field of the reference address is compared with the tag field of the slot. Then next is your again associative mapped cache, same continued. This is the example. This is mapped into the cache. This is the tag field and this is the word field. Then we have also discussed what are the advantages and what are the disadvantages of the associative mapping. The main advantage of associative mapping is that main memory can be placed into any cache slot. And the disadvantage is that more hardware and the more mechanism or huge algorithm is required for the mapping technique for associative mapping. So one is your huge overhead and next one is your huge algorithm or complex algorithm is used for the searching the tag memory in the path. Then next is your direct mapping. So second point is your direct mapping, that is each cache slot correspond to the explicit set of the main memory. That is your direct mapping. And there are 2 power 27 and 2 power 14 cache slots. That is, if I divide 2 power 27 and 2 power 14, that is 2 power 13 memory blocks or the main memory blocks can be mapped to the cache slot. This is the syntax. The tag is of 13 bits, slot is of 14 bits and word is of 5 bits. This requires 2 power 14. This is the same example. This is the same example that is discussed. Then we also discuss about the advantages and the disadvantages of the direct mapping. This is the disadvantage. Then next one is your SET-associative mapping. So third point is your SET-associative mapped cache. This also provides the flexibility of the associative mapping and the direct mapping. That is, it is a combination of the direct mapping and the associative mapping. We have discussed about the slot. These are the slots available. That is 2 power 13 sets. This point is also important. When an address is mapped to a set, the direct mapping scheme is used. Then associative mapping is used within a set. We have discussed about the field, that is it takes 14 bits, that is tag takes 14 bits in set associative and set takes 13 bits for set and the word takes 5 bits. This is your syntax for the set associative mapping. And we have also discussed about the advantages and disadvantages of the set associative mapping. The main advantage is that it is widely used in the today's microprocessors. Why? Because it is one of the most important technique, because it combines all the features of the associative as well as the direct mapping. Then we have discussed about the cache performance. That is today's topic also. That is the impact of the cache on the program performance. We have studied about the read and the write policies. There are two types of read. If data is available in the cache, simply forward to the CPU. But if the data is not available in the cache, then approach to the main memory, then there are two techniques that is available. One is your load through and one is your fill cache lines. Or fill cache lines. And there are two techniques for writing purpose, that is for writing into the cache. There are two techniques. In the same way, if data is available in the cache, there are two methods, write through and the write back. And if data is not available in the cache, there are again two methods, write allocate and write no allocate. Then we have discussed about the locality. That is, what is the locality? It is a tendency to reference data items that are near other recently referenced data item or that were recently referenced themselves. That is, if there is a data item that is nearby to the location or nearby to the data items, so that is done or that is known as the principle of the locality. That is, recently used methods or recently used data items are known as the locality. And there are two types of locality in cache memory. One is your temporal locality and one is your spatial locality. In temporal locality, if there is a data item that is referenced multiple times in the future, then we call it as a temporal locality. And the nearby location data or the reference data item is nearby of the memory location, and then this is known as the, or that is known as a spatial locality. Then we have discussed about the detail that is cache memory. It is a small fast memory that holds the operands and the instructions more or most likely to be used by the CPU. Then memory hierarchy is divided into three parts. One is your registers, then dynamic RAM memory, disk storage, as we discussed in the last class. This is the same pattern. First of all, there is a CPU and the main memory increasing gap, small memory RAM, because there is a huge gap between the CPU and the main memory. So L1 cache is inserted, L1 cache is introduced. Then L1 cache can be accessed almost as fast as the registers, typically 1 to 2 clock pulse cycle. Then due to the even more increasing gap, so there is a huge gap again between the CPU and the main memory. Then again a new cache is introduced, that is known as the L2 cache. Then L2 cache is attached to the memory bus or its own address bus. Then some high performance system, there is also a requirement for the another cache. Then there is another introduction of the cache memory, that is known as the L3 cache, that lies between or sits between the L2 and the main memory. It has a different arrangement, but the principle is the same. So last point says the cache is placed, means all the caches, L1 cache, L2 cache and L3 cache is placed both physically closer and logically closer to the CPU than the main memory. Then we will discuss about the cache lines or blocks. That is, cache memory is subdivided into the cache lines. That is, memory is divided into multiple chunks, that is known as the cache lines. So what is cache line or block? It is the smallest unit of the memory that can be transferred between the main memory and the cache. That is a line that connects the cache memory and the CPU and the main memory is known as the cache lines or blocks. Then we will discuss about the tag and the index. The dynamic field is known as the tag and the static field is known as the index. Means which can be changed with program to program is known as the tag, and which cannot be changed with the program to program, that is known as the index. Then we also discuss about the valid bit and the dirty bit. There are two types of bits available. One is valid, one is dirty bit. This is the example. This is a diagrammatical representation. This is the syntax, or this is the example, or this is the formula that we have discussed. Then we will discuss about the cache hits and cache misses. That is, if data is available in the cache memory, then that is known as the cache hit. That is, data is available, simply fetches the data and performs the operation. But if data is not available in the cache memory, then there is a cache miss. Then again, placement policies. There are three types of placement policies, that is associative, direct mapping and SET-ASSOCIATIVE mapping. Then we have discussed already, that is associative mapping, what are the advantages and what are the disadvantages. This is the direct mapping. Again, the advantage and the disadvantage of direct mapping. Then associative mapping or SET-ASSOCIATIVE mapping, that is a combination of the direct mapping and the associative mapping. Then we will discuss about the difference between the, or the differentiate between the lines, sets and the blocks. That is, in direct mapping, both the concept, that is set and the lines, are the equivalent, but in associative mapping, these are the different concept and then cannot be used as interchangeably. This is the block, this is the size, and this is the packet. So these are the three terms that is used in cache memory. That is your block, that is your size, and that is your set, and that is your line. So block is a fixed size packet of information that moves back and forth between the cache and the main memory. That is your block. And line, that is a container in a cache that stores a block as well other information. Then set, that is a collection of one or more lines. So there is a block, there is a line, and there is a set. Then what is the associativity? That is, if cache memory is related or address someone in the operating system, that can be placed with n number of operations, or n line, that is known as the associativity. Then we have discussed about the replacement algorithms. One is optimal replacement, one is random replacement. These are the techniques used First is FIFO, that is first in, first out. Then LRU, least recent used. Then LFU, least frequently used. We have discussed about these methods in the last class. Then we also discussed about the hit ratio and the effective access time, and the load through and the store through. This is the diagrammatical representation of the load through and the write through. Then these are the write methods. As I discussed, there are two types: if data is available in the cache and if data is not available in the cache. Then write through or write back. This is data is not available, write allocate, and not write allocate. This is the diagram that we have discussed already. This is the cache conflict. Then we will discuss about the cache coherency also, that is synchronization of data in the multiple caches. So that's all for today, yesterday's session. Now let's start with the today's session. That this section wraps up our discussion of memory hierarchy by studying the impact that cache have on the performance of the program running on the real machines. That is, it shows, or this topic shows the impact of the cache memory that is available, or impact of cache memory on the performance of the programs. First one is your memory fountain. The rate that a program reads data from the memory system is known as the read throughput, or sometimes the real or read bandwidth. That is, a rate by which program access the data from the memory is known as the read throughput or the read bandwidth. If a program needs n bytes or reads n byte over a period of s seconds, then the read throughput over a period is n divided by s. That is a read throughput, that is the time taken to access the data, that is divided by the total time, or that is divided by the number of seconds or time taken. That is usually or generally expressed in terms of megabits, that is MBs. These are the example. This is the example in C language, that is double data x LMS void test int elements int stride. That is a test function. This is a global array that is declared as a globally, that can be accessed or used by anyone. Then int I, then double result equals to 0.0. That is, result is a variable that is in double form, that is of decimal form, that is 0.0. Then again take another variable that is of type volatile and double, then the variable name is your sync, SINK. Then using the for variable or the for loop, starting with the 0, ending with the element, when element is less than I, then I plus equals to stride, that is I plus plus on the basis of stride variable, on the basis of stride value, then put the result equals to data I, that is using this value array, that is data I. First of all, it is data 0 displays the result, then data 1 displays the result, data 2 displays the result, data 3 displays the result, till it is less than the number of elements that is required. Then sync equals to result. So compiler does not optimize away the loop. Then curly braces closed. Then again it is using double run int size, int stride, double megahertz. That is, it takes three variables. One is of int, one is of another is also of int, and one is of double size. Again using the variable, that is size divided by size of double, that is in terms of memory it is used. Then it is form of the cache, that is used to inaugurate or initialize the cache. Then call test, this is a test function. The output will be stored in the C cycles. Then returns the value, that is convert cycle into MBs. This is the diagrammatical representation, that is L1 cache, L2 cache, L3 cache, and the memory. This is the pictorial representation, that is with the help of histograms. that is working set size, that is in bytes. That first is your main memory, then L3 cache, L2 cache, and the L1 cache, because L2 is very near to the CPU. A slope of the spatial locality. This is the slope of the spatial locality. Then next is your rearranging rows to increase the spatial locality. That is arranging the row with the help of matrices, that is n into n matrices. C equals to AB. For example, if n equals to 2, that is there are 2 rows and 2 columns, then C11, C12, C21, C22 equals to A11, A12, A21, A22 multiplied by the another 2 element 2 by 2 matrix, that is B11, B12, B21, B22. That is C11 equals to A11 multiplied by the B11, then again adding, then A12 is again adding to the B21. That is first row, first column, then first row, second column, A11, B12, A12, B22, and then there is an addition operation. Then second row, first column, that is A21, B11 plus A22, B21. This is the second row and the first column. Then second row, second column. So these are the rows and these are the columns. So first of all uses first row, first column, first row, second column. Then second row, first column, second row, second column. Then this is the second row, second column, that is A21, B12, A22, B22. This is how to rearrange the loops to increase the spatial locality. This is the example that is used. That is 6 versions of the matrix multiplication. These are the 6 versions. This is the core i7 matrix multiply performance. This is shown with the help of diagram or figure. Then exploiting locality in your program. So first of all, let's take with the help of another thing, that is PPT, that is your cache design. This is who cares about the memory hierarchy, that is processor versus the memory performance. That is the main topic of what is the performance or what is the impact of performance on the program, or impact of cache on the program. That is processor versus memory performance. So there is a CPU dynamic RAM gap. This is the gap between the dynamic RAM and the CPU. One is 1980, that is no cache in processor. Then 1995, that is a 2-level cache. Then this is the memory cache that lies between the CPU and the main memory. Then memory locality, that is memory hierarchy take advantage of the memory locality. That is a principle that future memory access are near past access. That is a assumption, or that is a principle that future memory locations or future memory accesses are nearby the past address or the past access. And this takes advantage of 2 types of locality. One is a temporal locality, that is near in time. One is a spatial locality, that is near in space or the distance. Then locality and the caching. So memory hierarchy exploits locality by the caching. That is memory hierarchy exploits the locality term, exploit the locality concept by using the caching, that is keeping the keeping the CPU closer to the memory, that is data likely to be used again. This is done because we build large slow memories and fast small memories, but we can't build large and the fast memory. If it works, we get the illusion of static RAM, that is your mean memory access time with the disk capacity. So this is the static RAM disk time, that is 1 to 5 nanoseconds access time, and dynamic RAM time is 40 to 60 nanoseconds. Then what is the disk? That is the access time measured in the millisecond. That is very cheap. This is a typical memory hierarchy. Main memory, on-chip cache, on-chip L2, H3 cache. This is one L1, this is your L2, this is your main memory, and this is your secondary memory, that is your disk. So then where is my program and data? This is the question. This is the cache fundamentals. Cache hit, cache miss. As you know, when data is available, that is cache hit, and if data is not available, that is cache miss. Then there is a hit time, that is time to access the higher cache. There is a miss penalty, that is times to move the data from the lower to the upper, then to the CPU. Then we have discussed about the hit ratio and the miss ratio. Cache block size, cache line size, instruction cache, data cache, unified cache, that we have already covered in the last class. These are the new topics. What is instruction cache? Cache that only holds the instruction. That is, cache is only required, or cache is only built for holding the instructions. That is known as instruction cache. Then next one is a data cache that only holds, or that only have the data, that is your data cache. So one is when only holds the cache memory, only holds the instruction, that is known as the instruction cache, and when only holds the data, that is known as the data cache. One is a unified data or unified cache that holds both the data as well as the instruction, that is known as the unified cache. L1 is unified, that is your a combination of the data and the instructions. Then cache characteristics. What are the characteristics of the cache? One is the cache organization, that is internal structure of the cache that lies between the cache and the, or that lies between the main memory and the CPU. Then cache access, that is how to access, or what is the access time that is required for the cache memory. Then cache replacement, that is what are the replacement algorithm that is used, like LIFO, LRU, LFU. Then write policy, as I discussed with you, when data is available, there are two concepts, write back, write through, and if data is not available, that is write allocate and write allocate. Then cache organization, that is where can a block data or the block can be placed in the cache. That is where can be, or the cache organization means where data can be blocked. So there are three techniques in cache organization, that is associative, direct, and SET-associative. Then cache access, how to access, these are the terms that we have discussed already. A typical cache has three dimensions. One is tag, one is index, and one is word. That is also known as the block offset. These are the block offset ways. There is a tag, there is a data that is available. Then which block should be replaced on a miss? That is direct mapping is easy, set associative or fully associative. Contains three parts, means it contains three parts for replacement on a miss, that is random, that is LRU, that is least recent used, and pseudo-associative. This is how to access a direct mapping, or how to use a direct mapping. This is accessing a two-way associative cache, that is your hit logic. Then this is a 64 KB, that is your 64 byte blocks. Then this is a cache organization. These are the word lines, these are the word lines, these are the bit lines. So these row format columns that is horizontal are known as the word lines, and the verticals are known as the bit lines. Then there is a tag array, there is a decoder, and there is a data array. So decoder lies between the data array and the tag array. Decoder is used for getting the input. Then column multiplexers, these are the column multiplexers, that is in red color. Then sense amplifiers, that is AMPs, that is in green color. Then there is a comparators, that is used for the comparison, that is in blue color. Then there is a output driver, this is the output driver, and this is your multiplexed driver, and there is a valid output is generated. This is the cache organization that contains word lines, bit lines, column multiplexer, sense amplifiers, comparators, output drivers, and at last valid output is given, and there is also a multiplexer drivers. Then At the right hand side, when there is a data array, there is a column multiplexer, sense amplifiers, but there is no comparators. And there is a output driver, that is your data and the output. Next is your evaluation of the cache access time via cacti plus the simulation, that is Intel wins via here. So this is a histogrammatical representation, that is how one-way and the two-way or four-way, eight-way data can be accessed. That is impact of the or evaluation of the cache via or accessing the time. This is your 16-bit, this is your 32-bit, this is your 64-bit, 128, 256. So these are the time, access time, that is 0.5, 1, 1.5, 2, 2.5. This shows 0.00346 miss rate, that is FAC00 Intel Core 2 Duo. Then 0.00366 miss rate FAC00 AMD operation. So this is the AMD operation and this is the Intel Core Duo operation. This is, or the dark line or the dark black color shows the one way, then two way, then four way, and then 8 way. What is cache access? That is how cache memory or CPU accesses the data from the cache memory. This is cache size equals to number of sets into block size into the associativity. So there are three concepts, that is number of sets into number of block size into number of associativity is known as the cache size. Then what is a cache size? If we have a direct mapping 120-bit cache with a 32-bit block. And what is the associativity? If there is a, or if we have a 128 KB cache with 512 sets and block size of 64 bytes. Then cache access. This is the 64 KB 4-way set associative cache, 32-bit address, byte addressable memory, 32-bit cache, block size, lines. How many tag bits? So this is a question, how many tag bits are required in this field? That is, where would you find the word at the address? This is again the requirement. Then 16-bit KB, that is your 4-way set associative, and 32-bit address byte addressable memory. Then what happens on the write? Next is your write operation. That is what happens if there is a write operation. So if data is available, in the cache, then there are two operations of the writing purpose, that is the write through and the write back. And if data is not available in the cache, there are two methods, that is your write allocate and no write allocate. So this is your write through, that is the information is written to both the block in the cache and the block in the lower level memory. That is, at the same time, the data is written to the cache memory as well as data is written to the main memory. Then next is your write back. The data is or information is only written to the cache memory, but data is not written to the next, that is your main memory. The modified cache block is then written to the main memory only when it is replaced. These are the two concepts, one is your write through and one is your write back. Then what are the pros or cons of each? One is your WD, that is your write through, that reads the message that do not need to write back evacuated line content. That is, whenever we use the write through, then there is a more chances of the misses. Then write back, that is no write of the repeated writes. WT combines with write buffers, so then don't wait for the low level memory. That is, write through is done very easily and efficiently. Then next is your what about the write miss? That is, if the data is not available, then what are the methods that is used for the writing purpose? So again, there are three methods, or there are two methods that is used. One is write allocate, one is no write allocate. What is write allocate? The data or the block is loaded into the cache on a write miss. That is a write allocate. And no write allocate is the block is modified in the lower level of memory but not in the cache. That is your no write allocate. So there are two concepts, one is write allocate and one is no write allocate. Then write buffer allows merging of writes. This is the write address. This is your grammatical or the diagrammatical representation. Then unified versus separate I plus D L1 cache. That is Princeton and Harvard architecture. So this is the concept, or this is the separate instruction caches and the data cache. This is our size block, that is 1 KB, instruction cache, data cache and the unified cache. 1 KB requires, or 1 KB needs 3.06%, 24.61% data cache and 13.34% unified cache. That is, if there is a data of 1 KB, then the instructions that is stored by the cache is only 3%, and if there is a 1 KB data is available is of only 24%, and if it needs or it stores both the data and the instruction, that it is only of 13%. In the same way, there is a different capacity, there is different requirement for the 2 KB, that is instruction is of 2%, data is of 20%, approx 20%, not exact 20%, but it is approx 20%, and the combination is of approx 9%. In the same way, 4 KB, 8 KB, 64 KB, and the 64 KB. This is the important, that is the 32 and the 64. Then 128 KB. Area limited designs may consider unified cache. Generally, the benefit of separating the caches are overlapping. Then cache performance, that is the cache performance that is affected the program, or that is affecting the program or the program performance. That is your cache performance. So first is your cache time, that is equals to the CPU execution clock cycle plus the memory store clock cycle. That is CPU time is equals to the, or the time taken for the CPU is equals to the, or fetching the data is equals to the CPU execution clock cycle. That is the time taken to execute the, or time taken to execute by the CPU depending on the clock cycle, plus the memory store clock cycle into clock cycle time. That is first of all adding the memory store and the CPU execution, and then multiplied by the clock cycle time. Then what is your memory or the memory store clock cycles? That is read into, or read x, read miss x rate, read miss penalty, plus write x, write miss rate x, write miss penalty. That is the time taken to read the data, including the miss, including the penalty, everything in case of the read as well as in case of the write, including every concept, that is write, miswrite and the miss penalty. Then next is your memory store clock cycles. Again memory access into miss rate into penalty. CPU time is calculated or used or modified or used or calculated as a CPU execution clock cycle plus the memory store, and that whole combination, that is the addition of these two, is multiplied by the clock cycle time. Then CPU or the cache performance again. Then CPU time, that is your IC into CPI execution plus memory store into the clock cycle, as I told you. Then CPU time again, IC, CPI execution, memory access per instruction, miss rate, cycle per time includes the hit time. Then average memory access time, that is your hit time, miss rate, miss penalty in clocks of the second. So these are the formulas that is used for increasing or showing the performance of the program, which affects the cache memory. Then how to improve, or what is the method that is used to improve the cache performance? First point says average memory access time equals to hit time plus the miss rate into the miss penalty. That is the average time taken for the memory to access is equals to the, or is equality to the, or equals to the hit time plus the miss rate into the miss penalty. That is equals to the hit time, that is the time that is used to hit the content, plus the miss rate into the miss penalty, that is in nanosecond of the clock cycle. How we are going to improve the cache performance? Then cache overview key points. Means what are the overview of the cache? These are the key points that we have discussed in this PDF. First one says CPU memory or the CPU memory gap is a major performance obstacle. That is, it is one of the hindrance, that is, there is a huge gap between the CPU and the main memory. This is one of the challenge in the CPU or the cache memory. Then cache takes advantage of the program behavior. That is, first of all, cache fills the gap, then it takes advantage or it exploits the locality terms, that is your, again, locality means your reference to the data item. Again, a combination of or is of two types. One is a spatial locality, one is your temporal locality. Then next point says designers has lots of choices. Means designer has lots of choices in the cache memory. It depends on the cache size, it depends on the block size, it depends on the associativity, it depends on the replacement policy and the write policy. So these are the different criteria or different concepts that is used in the cache memory. That is cache size, this is of different sizes, different block sizes, different associativity, different replacement policy like LRU, FLU. There are different write policies. Different write policies includes write through, write back, and write allocate, no write allocate. It depends on the data is available in the cache or if data is not available in the cache. Then next is we have studied about the time of program still only reliable performance measure. That is, time is also one of the reliable measure factor that is used in nanoseconds of the clock cycle. Then now this is your main topic, that is how to improve or improving cache performance. That is, what are the techniques that is used to increase cache performance, that increases the performance on the program. So let's see first of all with the help of book. This is exploiting locality in your program, as we discussed, that is used or that is done by exploiting the locality, that is covered or that is done by the how to exploit, that is covered by the cache memory. This says, as we have seen, the memory system is organized as a hierarchy of storage devices. That is, memory system contains hierarchy or multiple or the division of the storage devices with smaller, faster towards the top and the larger, slower devices toward the bottom. That is, it starts with the registers, then there is a cache memory, there is a main memory, and there is a secondary memory. On the top, there is the smallest memory, fastest memory. That is at the top. Then slowest devices towards the bottom, that is your secondary storage. So this is the that is of slowest devices and the larger device. So at the top in memory hierarchy, there is a small fast memory. At the bottom, there is a large and the slow memory. Because of this hierarchy, the effective rate that a program can access memory location is not characterized by the single number. So rather it is a wildly varying function of program locality. They can vary by orders of magnitude. Programs with good locality access most of their data from the fast access line. That is, it exploits the term of the locality or the meaning of the locality. Why? Because the program with the good locality or the good locality access can access the data from the cache memory. Next line says, program with poor quality or the poor locality access most of the data from the relatively main memory. That is, program with a good locality can access the data from the cache memory, and programs with the low quality or the low locality can access the data from the main memory. So programmers who need to understand the concept of or the nature of memory hierarchy can exploit this understanding to write more efficient programs regardless of the specific system organization. In particular, we recommend the following techniques, that is, focus your attention on the inner loop where the bulk of the computation and memory access occur. Then try to maximize the spatial locality in your program by reading data objects sequentially. Then try to maximize the spatial locality in our program by using the data objects. This is by reading the data object. This is, or temporal locality is done by using a data object as often as possible when it has been read from the memory. So spatial locality is done for reading the data, and for using the data it is used as a temporal locality. Now let's see with the help of another PPTs. Then next is you are improving the cache performance. So there are three methods for improving the cache performance. One of the method is reduce the miss rate. So whenever we want to improve the cache performance or improve the performance of the program in the cache, then one of the technique is reduce the miss rate. Then next reduce the miss penalty. Then next reduce the time to hit in the cache. So there are three techniques. Either we can reduce the miss rate, either we can reduce the miss penalty, and either we can reduce the time to hit in the cache. So these are the three techniques that is available to improve the cache performance. Then first starting with the reducing the miss rate. So these are the three classifying misses, that is 3 C's available that is used to reduce the miss. First one is your compulsory, then capacity, then conflict. So first one is a compulsory, that is the first access to a block is not in the cache, so the block must be brought into the cache. So this is the compulsory stage. So this is a compulsory stage, that is the first access to the block is not in the cache. That is first access that we access in the cache is not in the cache, or is not in the cache memory. So the block must be brought into the cache memory. These are also known as cold start misses or first reference misses. So this is a compulsory, that is the first access is not available in the cache memory. Then that is also brought into the cache memory. Then these are known as the cold start misses or the first reference misses. Then next is your capacity. If the cache cannot contain all the blocks that is needed during the execution, capacity misses will occur due to the block being discarded. So these are the three methods or the three classifying misses why there is a miss operation in the cache memory. Next point says, if the cache contains all the blocks needed during the execution of a program, capacity misses, that is, if there is a cache that does not contain or that cannot contain all the blocks, then capacity misses will occur due to the block being discarded and later retrieved. Next is your conflict. If there is a conflict, that is the block or if the block placement strategy is SET-associative or direct mapping, that is, if a programmer is using the associative or the direct mapping, then the conflict misses arises or occur because the block can be discarded. These are also known as or conflict is also known as the collision misses or interference misses. So there are three types of misses that is available in the cache memory. One is your compulsory, one is your capacity, and one is your conflict. Then these are the 3 C's miss rate, that is your first is your one way, two way, this is your capacity, this is your compulsory, this is your miss rates. Then how to reduce the misses? So first of all we have studied then what are the categories of misses, that is compulsory, capacity, conflict. Now how to reduce these misses? So first of all, compulsory misses, capacity misses, conflict misses. What can the compiler do? Means what is the requirement or what the compiler do to reduce the misses? Then first point says reduce misses via larger block size. That is we have to reduce the miss by using the larger block size. So this is a grammatical representation, that is how to reduce the misses by using the larger block size. So this is your starting from the 0, 5%, 10%. This is your requirement, that is your 4K, 16K, 64K, 256K. This is your block size, that is 16, 32, 64, 128, 256. And this is the miss rate. 16K cache, that is if it is of 16K, that is at this one, penalty, miss penalty for 16 byte block equals to 42. 32 bit is, this is a 32 bit, this is a 64 bit, this is at the 42. Then 32 bit is 44, this is of 16 bit, that is of 44. Then 48, 64 is of 48. Then miss rates are 3.94, 2.87 and 2.64. These are the miss rates and these are the miss penalties. Then how to reduce the misses via the higher associativity. So next method is used to reduce the misses. Next method is used to increase or hide the associativity. So first one is larger the block size. Next is increasing the associativity level. So this is your cache rule, that is your miss rate, DM cache size and equal. Miss rate, two-way associative cache size and divided by 2. Be aware, that is your note, execution time is only the final measurement. Will clock size increase or time increases? Then next one method is used to reduce the misses is the victim cache. That is how to get the fast time of direct map yet still avoid the conflict miss. So this is the grammatical representation. This is the victim cache. Any add buffer to place the data discarded from the cache. That is add the data. This is the CPU address data in and data out. This is a write buffer. This is a low memory. This is the cache memory. So one of the again next method is of using the victim cache by reducing the misses in the cache memory. Then next is your pseudo-associativity. So these are the 4 methods that is used to reduce the cache. This is one of the important method, that is how to reduce by using the pseudo-associativity that combines fast hit time of direct mapping and the lower conflict misses of a two-way set associative cache. So these are 2 techniques that is used in the pseudo-associativity. Then divide cache. On a maze, check other half of the cache to see if there or if so have a cache hit. So this is a pseudo hit time, miss penalty, there is a hit time. Then what are the drawback or what is the limitation? That it takes 1 to 2 cycles for approaching the or for using the or for reducing the miss. Then next is method of reducing the misses by hardware prefetching of the instruction and data, that I have already discussed. That is using the prefetching of the either data and the instruction is again the next method for reducing the misses. Example, instruction or instruction prefetching. Then prefetching relies on the extra memory bandwidth that can be used without the penalty. Then next is your stream buffer. Next, what is a stream buffer? That is allocate a stream buffer on a cache misses. Then run ahead of the execution stream prefetching and blocks into the stream buffer. That is, first of all, allocate a stream buffer on a cache misses. So if there is any miss, then allocates a stream buffer. Then next point says read ahead of the execution stream prefetching and blocks into the into the stream buffer. Then next is of searching the stream buffer in parallel with the cache access. If there is a hit, then move to the cache and prefetch the another block. This is the diagrammatical representation. There is a tag field, cache block, comparator, tag, cache block, comparator. This is your predictor-directed stream buffers that is effective for the next line and straight prefetching. Pointers allow stream buffer to follow any prediction stream. This is your impact of hardware prefetching on the Pentium 4. This is the impact. This is the diagrammatical representation. Then next method is reducing the misses by software prefetching. This is reducing the buffer by hardware prefetching. Now this is the next method that is used or that is done or that is used to reduce the misses by software prefetching data. So first is your data prefetch, that is load the data into the registers, then cache prefetch, then special prefetching instruction that cannot cause the faults. or false. This is your data prefetch. Then issuing the prefetch instruction takes the time. Then next is your next method is your again important method, that is reducing the misses by various operations or by various compiler optimization techniques. Then what are the optimization or what are the various optimization techniques? That is your first is your instructions, then reorder the procedure in memory so as to reduce the misses. So these are the instructions that is used, that is reorder again ordering the procedures into the memory so that to reduce the misses. So this is one of the method or one of the criteria that is used, that is reorder, that is again ordering the procedure in the memory so as to reduce the misses. So this is the concept by which we can reduce the misses. Then next is your profiling to look at the conflict, that is take the profile or look the profile to take at the conflict, then result in a 30% reduction in miss rate for an 8K I cache. So this results in performance or increase in the reduction in the misses by 30% for only or for the data size of 8K I cache. Then next is what are the data that is used for the reducing the misses. One is your reordering, then merging array, then loop interchange, loop fusion, and then blocking. So these are the method that is used. One is your reordering that results in 40% reduction, then merging array, this improves the spatial locality, then loop interchange that is used or to access data in order to store in memory, then loop fusion that combines two independent loops, then blocking that improves the temporal locality. This is the merging array example, as I have discussed already with the help of PPTs in the last two classes. First of all, int_val size key array. This is struct merge int_val key struct merge array size. So this is before merging and before the misses, and this is after the misses. Then loop interchange example. This is a loop fusion example. This is your blocking example. Then what are the key points? This is a formula that is used, that is CPU time equals to IC into CPU execution plus memory access divided by instruction into miss rate into miss penalty. Whole multiplied, this is your one term, and again multiplied by the clock cycle time. So this is IC into this term into clock cycle time. Then 3 C's. This is the compulsory C's, that compulsory, capacity, and conflict. And these are the 6 method or 7 method to reduce the misses, that is larger block size, higher associativity, victim cache, pseudo-associativity, hardware prefetching, software prefetching, and compiler optimization. Remember, danger of concentrating on just one parameter when evaluating the performance. So we cannot focus on only one parameter, but we can focus on another parameters also. Then next is your next technique for increasing the or improving the cache performance is your miss penalty. So till now we have discussed only one parameter, one method for reducing or improving the cache performance, that is your miss rate. Next one is your miss penalty, that is how to reduce the miss penalty. Till now we have covered how to reduce the miss rate. But before this, let's take a quick break, 5 to 10 minutes break, and then come back starting with the topic that is how to reduce the miss penalty. So let's take 5 to 10 minutes break. Next topic, that is improving the cache performance, how it will improve or how CPU will improve or computer will improve. The next method is here reducing the miss penalty. So first one is reducing the miss rate, then reducing the miss penalty. Now let's see. There are multiple techniques that is available for reducing the miss penalty, that is the penalty or the time taken to deliver or to reference to the next part, that is your reducing the miss penalty. One of the method is read priority over write on the miss, that is the priority of the read is more as or give the priority to the read operation over the write operation if there is a miss, that is if data is not available in the cache, then focus on the read operation instead of the write operation. By this way, we can improve or computer can improve the penalty, that is miss penalty, or reduce the miss penalty. First point says write buffer offers RAW conflict with main memory reads on the cache misses. That is, it gives or it conflict with the main memory that reads on the cache misses. Then if simply wait for write buffer to empty might increase read miss penalty by 50%. So if I'm waiting for the write buffer method to empty or to increase the speed, then it takes the penalty by the 50%. Then check write buffer content before the read. That is checking the writing purpose or checking for the writing purpose content before the read operation. If there is no conflict, let the memory access continue. So let the things continue or let the memory access continue. So these are the few methods that is used. One is a write buffer that offers RAW conflicts. Then if simply wait for the write buffer, that might increases the penalty by 50%. Then check write buffer content before the read. If there is no conflict, let the memory access continue. Then what is a write back? That is read the miss and may require write of dirty block. That is, I'm writing the back technique, that is a write back technique that read or that miss requires any number of or may require write of dirty block. Then normal, that is write the dirty block to the memory and then to the read. Then instead of copying the dirty bit to a write buffer, then do the read operation and then do the write operation. CPU stall less since it can restart as soon as read completes. This point says give the priority to the read operation instead of the write operation. There is a miss if there is data is not available in the cache memory. Then subblock replacement to reduce the miss penalty. The next point is here. So first point is here read the priority over the write. Then next point is here subblock placement, that is place the or the multiple or the chunks of the block can be replaced. That is a subblock placement to reduce the miss penalty. That is also known as sectoring. Don't have to load full block on a miss. Have bits per subblock. Then this is the grammatical representation, that is a valid bit is used before the tag bits. Then don't have to load full block on a miss, that is don't have to focus or don't have to load the full block on the miss, that is have bits per super block or sub block to indicate the valid bit. Then originally invented to reduce the tag storage. So this is the grammatical representation that stores how sub block replacement is used to reduce the miss penalty. That is your 200, 204, 0, 0, 1, 0. Then this is the early restart and critical word first. That is next method is to reduce the miss penalties to early restart and critical word first. These are the two techniques that is used either to early restart or using the critical word first. Don't wait for the full block to be loaded before restarting the CPU. You can early restart or you can use the critical word at the first level. As soon as the requested word of the block arrives, send it to the CPU and let the CPU continue execution. This is more useful with the large blocks. Special locality a problem. Often we need or we next want the next sequential word soon, so not always a benefit. That is an early restart. Then next is your non-blocking caches to reduce the stalls. That is using the non-blocking cache or lookup or the lookup free cache that allows or reducing the stalls on the system. This allows the data cache to continue to supply hit during a miss. That is, this allows the cache to continue or to give the supply cache or to continue to give the supply or the cache hit during the miss. Next, hit under the miss reduces the effective miss penalty. Then hit under multiple miss or miss under miss may further lower the effective miss penalty by overlapping the multiple misses. So these are the few techniques that is used to reduce the stalling, that is used to reduce the miss penalty. Assume stall on use and no stall on miss, which works naturally with dynamic scheduling but can also work with the static scheduling. So these are the techniques that is used, that is either uses the block available, no block available. So these are the techniques that is used in the or reduce the or it is used to reduce the blocking, or it is used to reduce the miss penalty. Then this is the value of hit under miss for SPAC. This is the percentage level that shows multiple benchmarks, that is SMV or SVM, percentage of the average stall time. This is your percentage wise, that is 0%, that is 0%, 10%, 20%, 30%, that is available. And these are the multiple margins, or these are the multiple points that shows multiple hits and the multiple miss. That is hit under 1 miss, hit under 2 miss, hit under 64 misses. Then next method to reduce the, or to use the, to reduce the next method to reduce the which one, that is known as the miss penalty, that is used for reducing the miss penalty, is using the multi-level cache. That is we can use the more than one, or the at the same time more than one cache, that is used to reduce the miss penalty. This is your L2 equation. This is your AMT, miss penalty, AMAT. This is the formula. Then definitions. What is a local miss and what is a global miss rate? Misses in the cache is divided by total number of memory access to this cache, that is known as the local miss, and the global miss rate equals to misses in the cache divided by the total number of memory access generated by the CPU, that is miss rate L1 and miss rate L2. That is your global miss rate. This is the diagrammatical representation of L2 local miss rate, pretty high. This is our local miss rate, global miss rate, and single cache miss rate. So this point, this is your local miss rate, this is your global miss rate, this is your single cache miss rate. Then L2 cache more important than the latency. Why? What is the reason? This is the reason that shows by using the diagram. Then multi-level cache continue. Design L1 and L2 caches in concurrent or concert. Then property of inclusion, that is these 3 points, or the first 3 points says L1 has a cache local miss rate of 10% and L2 has a local miss rate of 40%, and L2 is a higher priority access time as compared to the L2, or L1 has a higher priority time as compared to the L2. Why? Because L2 is so, or the very near or close to the CPU. Then design L1 and LK caches concept. Then property of inclusion. If it is in the L2 cache, is it guaranteed to be in one of the L1 cache? That is, if data is available in the L2 cache, then it is mandatory, or it is important to know that data is also in the L1 cache. That simplifies the design of the consistent caches. Then next point says L2 cache can have different associativity or block size than the L1 cache. This is the multi-level cache, that is L1 and the L2. This is the difference or comparison between the L1 and the L2 cache. So L1 has a high priority as compared to the L2, and L1 and the L2 are used in the concurrent. Then reducing miss penalty summary. So this is the summary that what are the techniques that is available to reduce the miss penalty. 5 techniques are used. One is read priority over the write, then sub-block replacement, then early restart and critical word first, then non-blocking cache, then multi-level of cache. So this is the last slide. That is, next is your reduce the time to hit in the cache. So these are the 3 techniques that is used to improve performance. First is your reducing the miss rate, then reducing the miss penalty. These contains multiple, or the 6 to 5 or 5 to 6 number of method that is used to reduce the miss rate and reduce to, or used to reduce the miss penalty. Then next is your simply reduce the time to hit in the cache. So these are the 3 techniques that is used to increase the cache performance. Now let's see. Next part is your summary, that is already finished. The summary is said the basic storage technologies are random access memory, non-volatile memory, and disk. RAM comes in two forms, static RAM and dynamic RAM, and is used for the cache memories both on of the chip. Dynamic RAM is slower and the less expensive. So the comparison among the various memories. Non-volatile memories, also known as a read-only memory, retains their information even if the supply voltage is turned off. That is, if the power has gone, it can retain the data. Why? That is of non-volatile nature. Then next is your next point says there is again solid state disk, that is based on the non-volatile flash memory, are becoming increasing attractive alternative to the waiting disk for some application. So these are the techniques, so these are the memories that is used in the day-to-day scenario, is used in the C. These are the problems that is used. These are the solution to the problem. Uh, this chapter contains 47 problems and then solution to the problems. These are the mapping technique that is used. Then we have studied about the cache access. These are the cache access. What happens on the write? Then unified versus separate I plus D. Then cache performance. We have studied about the different formulas that is used. This is your cache or CPU time. Then how to improve the CPU performance. This is your cache overview. Then we studied about the three techniques, that is how to improve the cache performance, that is either by reducing the miss rate or either reducing the miss penalty or either reducing the time to hit in the cache. And reducing the miss, we need 3 misses or kinds of misses, that is compulsory, capacity, conflict. These are 3 misses. Then how to reduce the misses? These are the techniques that is used to reduce the misses. These are the techniques that is used to reduce the misses. Then how to reduce the miss penalty? These are again the techniques that is reduce the miss penalty. We have studied in the today's class. These are the 6 methods that is used to reduce the penalty. Then last one is reduce the time to hit in the cache. So that's all for today's session. Now, if you have any doubt, then please text the doubt and I will answer you. Now, if you have any doubts, then please text the doubt and I will answer you. That's all for today's session.